As a prelude to an upcoming series on the quantum interpretations, this video will give an analysis of the values of Bell's inequality, or Bell's theorem, according to which you have to choose between reality as advocated by people like Einstein and Bohm, and the quantum mechanics of Bohr, Heisenberg, etc. Since its introduction in 1964, Bell's inequality has become more or less a touchstone for any new ideas about the workings of quantum mechanics. One of the first reactions to the introduction of our series on the quantum solutions read, amongst other things, what does it say about Bell's inequality? That we are going to do now, and its conclusion will be that in some sense both parties are right, because Bell's inequality, though true, contains an invalid assumption of physical reality, which also makes realism true. Bell's inequality was more or less the final stage of what has become known as the discussion between Bohr and Einstein on the completeness of quantum mechanics. These pictures of them busy at it were taken by a colleague Paul Ehrenfest, who undoubtedly also participated. His home in Leiden, the Netherlands, was a focal point of these discussions. And according to everybody, the discussion was won by Bohr, as here voiced by colleague Byte. It all started with a paper by the trio Albert Einstein, Boris Podolsky and Nathan Rosen, together with its follow-on by Niels Bohr, in the meantime gotten so famous that they are called the EPR papers. In the first one, the authors construct a thought experiment whereby both position and momentum of a particle can be sharply measured, while quantum mechanics says that cannot be done. So, they said, quantum mechanics must be incomplete and be supplemented with extra parameters that later got the name of hidden variables. In his reply, Bohr made the thought experiment explicit, coming up with illustrations like these, and refuted the EPR version, leaning to the saying that Bohr had won the discussion with Einstein. However, a definite conclusion lacked, since practical experiments were not feasible. Later, David Bohm came up with a version that doesn't use position and momentum as the pair that can or cannot be measured together, but one that uses up and down or spin of two particles that initially form a state that has spin is zero. For the separated states then goes that if the one is up, the other is down, vice versa. This is what one calls that the separated states are entangled, which is something that conceivably could be made into a real experiment. Bohm's example uses spins, but one could also do it with any correlated pair, like pairs of glass as in this example by colleague Arvin Esch. So these are more or less mechanical or classical calculations. One can also calculate the correlations within the quantum mechanical formalism, and these outcomes differ from the classical ones. These rather complicated calculations were done by John Bell, who developed a mathematical equation for the correlations, which the classical case would obey and the quantum mechanical one would violate. As mentioned, over time Bell's inequality has become more or less a touchstone for any new ideas about the workings of quantum mechanics, and, since it is mathematics, also has become one of the pillars for the mathematical look at it, which is, as a principle of approach, more or less the opposite of the practical view. So let's have a practical look at the inequality and its associated measurements. First, the actual calculations. Because in real life you don't have the ideal situation of particles that are neatly aligned with the polarizers, one has to find correlations between the numbers detected for a number of polarizer settings. We are lucky not to have to do these calculations, because they look like the ones shown in the illustration. Then the actual measurements. These are as laborious as the calculations, because one has to exclude all possibilities for the situation at one detector to influence what happens at the other, which one finally achieved by using multiple detectors at each end and channel switching such that any influence would have to travel faster than the speed of light, or so one thought. Because in the previous series on the solution of the quantum problems, we had to introduce two basic steps that here also changed the game. The equipment must not be seen as merely a tool to record numbers, but as an active part in the process, by looking at its individual microscopic particles, see specifically part 6, or just look at the illustration and use your common sense. And secondly, One has to define the workings of quantum mechanics as an interaction between two particles. In the case of doing a measurement, one particle being the studied one and one from the equipment. The waves involved in this interaction are related to the Dirac equation and therefore permanently present. The shown interference wave then obeys the Schrödinger equation, see part 5 of the previous series. Together with the first step, this solved the measurement problems. But the specifics aren't necessary here. Just defining a basic two-particle quantum interaction that is active permanently is enough. With this knowledge, let's have a similar look at the Bohm experiment. On top is the basic layout. The equipment that is the source of the singlet particle duos in the middle, and the two pieces of equipment to measure the separated particles once they split up, that use polarizers to select the spin direction followed by detectors. And at the bottom, what is supposed to happen? Once one particle is measured in the chosen direction, the other one immediately takes the opposite direction. If one is transmitted by the polarizer, the other one is blocked. Here's how this looks when one uses the previous steps. The quantum mechanical interaction is between the measured spin-related particles and those of the polarizers that do the selecting before the counting. This immediately shows that the quantum mechanical description is the right one. No further arguments are necessary. The separate particles are entangled at the source and still entangled when reaching the polarizer's annexed detectors. And it also immediately shows that this quantum mechanical outcome is determined by the individual particles in the equipment that act as parameters that were hidden if you had forgotten that the equipment is built up from them in the first place. And one could easily call the separate microscopic wave functions pilot waves. So both views are right, and no further calculations, inequalities, complicated measurements, etc. are necessary. So if you ask the final question, which of Bell's preconditions is right? It is separability. That is separability of measurement, not locality in the sense that things travel faster than light. So Einstein was also right. Now isn't that a relief? No spooky action at a distance. And this EPR situation is not unlike the double slit experiment. The particle in the double slit case corresponds to the singlet states in the source of the EPR case. The two beams towards the slits correspond to the two beams of interaction of the singlet states with the two detectors. And in both cases, the outcome is determined by the measured particles being in interaction with all of the microscopic particles in the equipment. This goes for any arrangement with multiple detectors, etc., because this equipment has to be set up before the experiment can start. So all channels are already there before any switching between them can start. Attempts to circumvent this can be seen as complicated versions of Maxwell's demon. A mixture of two gases is split in their constituent parts by a demon that watches the gate in the wall that splits the mixture in halves and opens the gate if it sees the right particle coming towards it. So Bell's theorem, though not untrue, is not very relevant because what it wants to prove mathematically can also be proven physically, and the latter always has the preference because it can be measured and thereby be confirmed as a part of reality, or not. No mathematical proof provides any certainty about reality. And this lesson should be known from the historic example of the proof of the completeness of the quantum mechanics of the Copenhagen interpretation by the most highly regarded mathematician John von Neumann, which as a proof is correct, but doesn't pertain to reality, because it was shown to contain a hidden assumption that wasn't physically practical, one of the pitfalls of any mathematics. The conclusion, where the standard story is that Bell's inequality forces us to choose between quantum mechanics and realism, it has been shown that quantum mechanics can be neatly reconciled with reality as long as you take into account the reality that macroscopic equipment is built up from microscopic particles. In following videos, what has here been found on the relation between mathematics and physics and the relation between the macroscopic and macroscopic worlds will be expanded. The results from that will then be applied to the other quantum discussions and interpretations.